Okay, I got cut off because I have a 10-minute limit for Screencastify. So part 2, we have a skydiver falling faster and faster. We've just learned that the net force on that faster and faster falling skydiver, is decreasing. So now we ask, what happens to the acceleration of the skydiver as she falls faster and faster through the air? Well, if we are going to decide that her net force decreases, Newton's second law tells us that her acceleration must also decrease. So it goes like the following. The skydiver falls, going faster and faster. As she falls, air resistance increases more and more. As her air resistance increases, the net force on her decreases until air resistance is equal to weight. At that point, she stops accelerating. Her acceleration has decreased until net force is equal to 0. At that point, she's at terminal velocity. She stops accelerating and she falls for the rest of her dive at constant velocity. This is not dealing with the opening of the parachute. You'll work through a worksheet question where you consider what happens after the opening of a parachute. Okay, this is the last free fall or non-free fall question. Consider a heavy and a light person jumping together with the same size parachute from the same altitude. Who will reach the ground first? So in order to answer this question, we need to know that the same size parachute from the same altitude means these two people will experience the same drag force at the same speed. So they'll end up with the same amount of upward air resistance. So who reaches the ground first? If this was free fall, we would say they reach the ground together. But in this case, the heavy person has a larger downward pull from gravity. The heavy and the light person end up with the same drag speed. So the same drag force. So the heavier person ends up with a larger net force and a higher terminal velocity. Larger net force, higher terminal velocity. And so this heavier person will reach the ground first, will accelerate more. If we could evacuate the air from a tube, we could look at the drop of a coin and a feather. The feather will reach terminal velocity very quickly, almost instantly, and it will fall then slowly at a constant speed. The coin falls quickly and air resistance doesn't build up to its weight over short falling distances. So the coin will reach the bottom first, and the feather will reach the bottom second, because the feather will fall with lots of air resistance affecting its fall, whereas the coin will fall with little air resistance affecting its fall. The strange little animation here was showing the coin and the feather falling in an evacuated tube. If we can evacuate the air out of the tube, so there's no air in the tube, it is now a vacuum. There's no air resistance on either or both objects. If they're falling in a vacuum, they're truly in free fall, and the coin and the feather fall together and hit the ground together. Unfortunately, we don't have an apparatus like this to see, so we'll just go with the animation. And this is the end of the lecture. You should now have all slides, all pages of the Chapter 5 lecture notes filled out.